Unit 5, Section 6, Rates of Change and Linear Approximation. Session objectives. By the end of this session, the student will be able to 1. Find rates of change. 2. State and use linear approximation formula. Rates of change. You are given a function y is equal to f of x, then its derivative dy over dx represents the rate of change in y with respect to x. That is, if we take y to be a quantity which varies with x, then the rate of change of y with respect to x is dy over dx. And the quantity y can be taken to be, let's assume, a quantity of bread which varies with x, the cost of sugar. So the change in the cost of bread with respect to the cost of sugar can be written as dy over dx. Now you should know that the quantity y is either increasing or decreasing depending on the rate of change dy over dx. If the rate of change dy over dx is positive, then the quantity y is increasing. However, if the dy over dx is negative, then the quantity y is decreasing. Rates of change. Example 1. Water is flowing out of a bath, and the depth of the water y centimeters at time t seconds is given by the relation y is equal to 16 minus 1 over 8t minus 1 over 4t exponent 3. We have to find the rate at which the depth of water is decreasing at 2 seconds and at 3 seconds. Now, to find the rate at which the water is decreasing in the bath, we differentiate the given relation with respect to time. So it implies we are finding the rate at which the water in the bath decreases with respect to time. And that gives dy over dt to be negative 1 over 8. This is because when the constant 16 is differentiated, it gives 0. And differentiating negative 1 over 8t gives the negative 1 over 8. Then minus 3 over 4t exponent 2. That is when we differentiate the term 1 over 4t exponent 3. It gives 3 over 4t exponent 2. Now, at the instance when the time is 2 seconds, then we substitute that 2 into the rate of change dy over dt. And that gives dy over dt to be negative 1 over 8 minus 3 over 4 into braces 2 exponents 2, which gives negative 3 1 over 8. At the instance when t is equal to 3, then our rate of change dy over dt is equal to negative 1 over 8 minus 3 over 4 into braces 3 exponent 2, which is equal to negative 6 7 over 8. Hence, the depth of water at 2 seconds and 3 seconds is decreasing at positive 3, 1 over 8 centimeters per second and 6 whole number 7 over 8 centimeters per second. Now, we can see that at the two instances initially, the results were negative. But the negative only indicates that the rate of change or the quantity is decreasing, and hence we write the final answer in absolute terms. Example 2. The radius of a spherical balloon is increasing at 0.5 centimeters per second. At the instant when the radius is 4 centimeters, find the rate at which A, the surface area is increasing. B, the volume is increasing. Solution. We let R to be the radius of the balloon and A centimeter squared to be the surface area of the balloon and V centimeter cubed to be the volume of the balloon. Now, when we study the question carefully, we are giving the R over the T, that is the rate at which the radius increases with respect to time in the question. And we are interested in finding the rate at which the surface area increases with respect to time, the A over the T. So we use chain rule, which is the A over the T is equal to the A over the R times the R over the T. But in the question, we are giving the R over the T to be 0.5. But for us to find the A over the R, we need to know the formula for finding the surface area of a sphere, which is A is equal to 4 pi R squared. Now, differentiating A with respect to R, that gives the A over the R is equal to 8 pi R. Now, putting the R over the T and the A over the R into the chain rule formula, we have the A over the T to be equal to 8 pi R times 0.5, which gives 4 pi R. Now, at the instant when R is equal to 4, we substitute 4 into the A over the T, which gives the A over the T to be 4 times 4 pi, which is equal to 16 pi. We can therefore say that the surface area is increasing at the rate of 16 pi centimeters squared per second. B. To find the rate at which the volume is increasing, we have to find the V over the R. And to find the V over the R, we have to know the formula for finding volume of a sphere, which is V is equal to 4 over 3 pi R cubed. Now, differentiating V with respect to R, in order to obtain the V over the R, we have the V over the R is equal to 4 pi R squared. Now, looking at our chain rule, our dV over the T is equal to the V over the R times the R over the T. But we know the R over the T, which is 0.5 or 1 over 2. And the V over the R is obtained by differentiating the volume with respect to radius. And hence, substituting the V over the R and the R over the T, then we have the V over the T to be equal to 4 pi R squared times half, which is equal to 2 pi R squared. Now, at the instant when R is equal to 4, we substitute R is equal to 4 into the V over the T, which gives the V over the T to be 2 pi 4 into braces squared, which is simplified to have 32 pi. And we can now say that the volume is increasing at the rate of 32 pi centimeter cubed per second. Linear approximation. This is a concept of an approximation of a general function using a linear function. Or linearization is the process of taking the gradient of a nonlinear function with respect to all variables and creating a new linear representation at that point. In other words, we use the target line A, comma, f of A, an approximation to the curve y is equal to f of x, where x is close or near to A. Now, the formula used for linearization or an approximation is given by L of x is equal to f of A plus f prime of A. then multiplying x minus a. Linear approximation. Example, find the linearization of the function f of x is equal to the square root of x plus 3 at a is equal to 1, and use it to approximate the number the square root of 3.98 and square root of 4.05. Now, to find the linearization of the function f of x, we first have to differentiate the given function. And hence, finding f prime of x, that gives half into braces x plus 3 exponent negative half. That is using the power rule. And knowing that the root of x plus 3 is the same as into braces x plus 3 exponent half, which gives 1 over 2 root x plus 3. And also finding f of 1, meaning in the function f of x, wherever there is x, we put 1, which gives f of 1 equals the root of 1 plus 3, which is the root of 4, and root of 4 is 2. Now, to find f prime of 1, that is the derivative of f of x at 1. In the function or the derived function f prime of x, wherever there is x, we put 1. And hence we have 1 over 2 root 1 plus 3. And root 1 plus 3 is root 4, which is 2. So 2 times 2 gives 4. And hence the denominator 4. So therefore, f prime of 1 is 1 over 4. Now putting f of 1 and the f prime of 1, that is the derivative at 1, into the linearization formula, we have L of x equals f of 1 plus f prime of 1 multiplying x minus 1. Now f of 1 is 2. Then plus f prime of 1, that is the derivative at 1, is 1 over 4. Then multiplying x minus 1, which gives 7 over 4 plus x over 4. Therefore, the root of x plus 3 is approximately 7 over 4 plus x over 4. And hence, using our solution or our answer to approximate the root of 3.98, we need to find x in this. And to find the x, we equate x plus 3 to 3.98 and solve for x. So if x plus 3 is equated to 3.98 and solving for x, x gives 0.98. And wherever there is x, we replace it with 0.98, which gives 7 over 4 plus 0.98 over 4. And since the denominators are the same, we add the numerators. That gives 7.98 divided by 4. And it is 1.995. And also, for the root of 4.05, we equate 4.05 to x plus 3 and solve for x. So solving for x in x plus 3 is equal to 4.05 gives x is equal to 1.05. And wherever there is x, we put 1.05, and hence 7 over 4 plus 1.05 over 4. And again, since the denominators are the same, we add the numerators, which gives 8.05. Then we divide it by 4, which results to 2.0125.